So we see that the self inductance acts as an electrical inertia. Now today we going to derive the different formulas for the self inductance. So first, that is the self inductance of long solenoid. So let us consider a solenoid. We have L, that is equal to phi upon I. So phi is the magnetic flux and I is current flowing through that circuit. Then self inductance is given by equation L, that is equal to phi upon I. Suppose the solenoid has a number of turns M, and if the magnetic flux associated with the single turn of that solenoid, then we have L, that is equal to N phi B upon I, since phi, that is equal to N into phi B. So phi, that is the total flux associated with the solenoid, if N are the number of turns of that solenoid, and phi B the magnetic flux associated with the single turn of that solenoid. But N phi B, N that is total number of turns of the solenoid. So N is equal to NL, whereas capital N, that is total number of turns of the solenoid, and small n, number of turns per unit length of the solenoid. And if L is the length of solenoid, then we have capital N, that is equal to NL. And by definition of magnetic flux is given as the product of magnetic induction and area. Therefore we have phi B, that is equal to B into A, where B is the magnetic field or induction of magnetic field and A is area. But in the topic, the magnetic effect of electric current, we see that the magnetic field inside the solenoid is given by equation B, that is equal to mu 0 N into I. So where mu 0 is the permeability of free space, N number of turns per unit length of the solenoid, and I, that is the current flowing through that solenoid. Now substitute the value of B. So B, that is equal to mu 0 small I that is a induced current, so into A. Therefore N phi B is equal to N into L mu 0 Ni into A. Therefore L is equal to, so what is L? That is N phi B upon A, I. So divide this equation by I, we get L, that is equal to NL mu 0 Ni A divided by I. So I get cancels, and therefore we have mu 0 N square L into I. So what is mu 0? That is the permeability of free space. What is N, small n, that is the number of turns per unit length of the solenoid. What is L? That is the length of that solenoid. And what is A? That is the area of solenoid. So L is the self inductance of a long air cored coil. L is the length. So this is the length of that solenoid. Then what is A? That is the area of cross section, LA. What is small n? Number of turns per unit length, and I is a current flowing through that solenoid. So this is the expression for the self inductance of the long solenoid. So what is that expression? L, that is equal to mu 0 N square L into A. So therefore the self inductance of a solenoid depends upon the number of turns per unit length of the solenoid, then L, that is the length of solenoid, and that is the A, that is the area of cross section of that solenoid. So this is the expression for the self inductance of long solenoid. So we have the self inductance of long solenoid L, that is equal to mu 0 N square L into A. Then self inductance per unit length. So divide this equation both sides by L, then L get cancels. So self inductance per unit length is equal to mu 0 N square into A. But area, if the cross sectional area is in a circular form and R is the radius, then A, that is equal to pi R square. So if r is the radius of that solenoid and which is half the its diameter, so this can be written as pi into d by 2 bracket square, and that is pi d square by 4. Now substitute this value in above equation of A, we get self inductance per unit length of the solenoid is given by equation mu 0 n square pi d square by 4, and this equation is useful for the further derivation, that is the self inductance per unit length of the solenoid is given by this equation in the terms of diameter, where L, capital L upon L, that is the self inductance per unit length, is equal to mu 0, that is the permeability of free space, small n square, that is number of turns per unit length of the solenoid, pi d square, d that is the diameter of solenoid, divided by 4, where d is the diameter of solenoid. Now we have to derive the expression for self inductance of toroid. So what is the solenoid? If the solenoid is bent to form the endless, then it is converted into toroid. So this is the difference between solenoid. So this is a toroid carrying a current I. Suppose this is a toroid. I draw here a small figure of that. Suppose this is a circular ring, and if the coil is wound on this, and suppose I is a current flowing through that solenoid, toroid, then the self inductance of that toroid is given by equation mu 0 by 2 into n r square divided by 2. So what is the mu 0? That is, if there is air core, that is the permeability of free space. What is capital N? Total number of turns of that toroid. What is R? R, that is the area, radius of cross sectional area of that toroid. Suppose this is a cross sectional area. Suppose this is cross sectional area, then this radius is called as a, this is the cross sectional area, then its radius is called as a small r. And what is R? That is the major radius from the center to its mean, that is the axis, that is the major radius. So this is the expression for self inductance of toroid, where mu 0 is the permeability of free space, n total number of turns of toroid, then r radius of cross section of toroid, capital R major radius of toroid, and this is about the self inductance of toroid and solenoid. So next article, when the number of inductors are connected in a circuit, they may be connected into two combinations, that it may be connected either in series or in parallel. So the next article, that is inductances in series and parallel. So when inductances are in a previous article, we see that the resistances in series, we also see that the capacitors in series and parallel combination. So what happens when the number of inductors are connected in series? That is, the inductors are connected one after another. So in this figure, there are three inductors, L1, L2 and L3 are connected in series. Then their effective inductance is given by equation L, that is equal to, as like that of resistor, L1 plus L2 plus L3. In general, if the n inductors are connected in a series, then the L is given by equation L1 plus L2 plus L3 dot 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 Ln. So this is the expression for effective inductance of the series combination of inductors, that is the L suffix S is equal to L1 plus L2 plus L3 plus dot 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 plus Ln. So it is clear that to increase the inductance of circuit, the series combination of inductance is required. because the effective inductance is greater than individual inductance of any inductor. So this is the first combination, that is the inductors are in series. Then the next, that is the inductors in parallel. So when the number of inductors are connected between the two common points, then that arrangement is called as a inductors in parallel. So let us consider again a three inductors L1, L2 and L3 are connected between two common points, then that arrangement is called as a parallel combination. Then their effective inductance is given by equation 1 upon L, that is equal to 1 upon L1 plus 1 upon L2 plus 1 upon L3. That is the reciprocal of effective inductance of the parallel combination is equal to algebraic sum of reciprocals of individual inductances. So in general, if there are n inductors are connected in parallel, then it can be write as 1 upon L suffix p, that is equal to 1 upon L1 plus 1 upon L2 plus 1 upon L3 plus dot 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 plus 1 upon Ln. So the reciprocal of effective inductance is algebraic sum of or equivalent to algebraic sum of individual inductances. So it is clear that 1 upon Lp is always greater than 1 upon L1 or 1 upon L2 or 1 upon L3. Therefore Lp is always less than L1 or L2 or L3. Therefore the effective inductance or resultant inductance of parallel combination is always less than any individual inductance. So this parallel combination of inductance is used to decrease the inductance of circuit. So this is about the series and parallel. So in this lecture we see that the concept of self inductance, different definitions of self inductance, then the formula of self inductance, then its unit, then we see the different derivations of self inductance of the solenoid, then the self inductance of toroid, and then the inductances in series and inductances in parallel. So this is all about the self inductance.